Now I want to talk about Markov chain. All right, so let's consider binary state Markov chain. So there are two states, 0 and 1, and this graph tells you the jumping probability. So from state 0 to 0, it jumps. It stays with the 0 state with the probability 1 minus p. It jumps to state 1 with the probability of p. And from state 1 to 0, q, state 1 to itself, 1 minus q. And then we want to consider Markov chain x0, x1. There is a typo, so I forgot. This has to be included right here. x0, x1, x2, and so on, all the way up to n. And then we can let n goes to infinity as well. And this one, there is a transition matrix P, and the initial distribution pi, and stationary distribution S. So this can be, the relationship between them can be obtained by considering this simultaneous equations. So for example, probability that x1 is equal to 0 can be written as using total probability theorem, probability of x1, 0, and x0 is equal to 0. And then using conditional probability, it can be written this way. And starting from 1 to 0, it can be written this way. So if I say this one more time, for example, you can show that this probability x1 is equal to 0 is equal to, using total probability theorem, it is equal to probability x1 equal to 0, x0 equal to 0 plus x1 equal to 0, x0 equal to 1. And then basically from here you can obtain this part right here. From here you can obtain this part right here. Okay, so that's that. And once I have done this, then you can combine the two things together, and then we can say that x1 equal to probability x1 equal to 0, probability of as x1 equal to 1, and then we think about this part. So that part is jumping from 0 to 0 is 1 minus p, and then this one here is 1 to 0, so it is q. And this one here, right here, when the x1 is equal to 1, it came from 0, right? So 0 to 1, which is p, going this way, and then staying probabilities 1 minus q. And then this one, starting from state 0 and 1. Okay, so that's the basic equation, and then we let this initial distribution to be denoted as pi, this transition matrix as P, and this one we call it I believe that one is called T. Okay, so this is called T1. Okay, so if I jump once, this is that. If I jump twice, then we come from here, and then when I evaluate this, T is equal to P pi, so this is P square pi, and so on. So in general, Tn is equal to Pn pi. So that's general equation. If I let n goes to infinity, then we come up with a stationary distribution. That's what we call S vector x. We will call S0 and S1. And this is a stationary distribution. All right. So that's what I had in previous page. So distribution at any time point n is P nth power times pi. And the stationary distribution S is obtained when we let n goes to infinity. So by definition of stationarity, basically, S is equal to PS. So jump doesn't change the distribution anymore at large n. So if I apply this to solve for stationary distribution, then we can find the S exactly. So here is an example. So P is given to be 0.1, Q is 0.3, and P is given to be this transition matrix. And then when you take the P infinity, then this come out this way, and there is a stationary distribution appearing right here. And also we can use this equation to solve for stationary distribution. And for example, in this particular case, let me see. In this particular case, stationary distribution S can be found. 0, S1, right? And then P in this case was 0.9, 0.3, and 0.1, 0.7, that's our P. And then we multiply this, we get S0, S1 again. And since S0 plus S1 is equal to 1, we have a 1 equation. And then from this equation, we get another equation. So let's take a look at S0. S0 is equal to, probably we use, so this part is 1 minus P, and Q, 1 minus Q. So we use that one, general form, to find out what stationary distribution expression look like using P and Q. So S0 is equal to 1 minus P times S0 plus Q times S1. So you get another equation. So from here, we know that this is S0, P S0 plus Q S1. And then, what should I do? Okay, then here we move S to the other side, and this to the other side, then it is P S0 equals Q S1, and then from here, let's call S0 to be Q over P S1. So we obtain this one. Now we put this into equation 1, and then we get Q over P plus 1 times S1 is equal to 1, and then S1 is nothing but P plus Q, right? So that's that. And utilizing this equation number 1 again, then S0 should be Q over P plus Q. So we obtain the general expression, and then if I apply this P and Q, then S1 is equal to P is 0.1, and P plus Q is 0.4, so this is 1 over 4. Then S0 should be 3 over 4. So that is exactly what we have right here. So that's the little bit about the Markov chain. Okay, clear it. And then we can talk about this thing now. We can consider pi uniform distribution. So pi we can let half and half. Okay, and then utilizing this setting right here, we can notice that entropy decreases toward the distribution entropy based on this. So basically entropy decreases to 1/4, starting from half. So this one is 1, and this one is smaller than 1, so we are decreasing as Markov chain evolves. Okay, you can also have an increasing case. So for example, let's say we have initial distribution. Let's say let's have a pi which is equal to non-uniform distribution. So I want to make it extreme. Let's say 0.1, 0.9, right? And then stay with the stationary distribution, this one. And then in this case, we start off with the entropy of 0.1, and then we are increasing to entropy of 1/4. So in this case, we are increasing toward h of s. So we can make the Markov chain, the entropy of Markov chain, either increase or decrease. We can design such Markov chain. I have given an example using binary Markov chain. We can do ternary Markov chain or quaternary, quad, or whatever dimension. We can design such Markov chain. Okay. Well, having said that, we now move to the second law of thermodynamics. Second law of thermodynamics says that entropy is non-decreasing. So basically, entropy of an isolated system, like we have considered in previous case, but this one in thermodynamic ways is non-decreasing. So basically, entropy generally increase or stay. That's what it says. And the one famous example regarding this one is ink dropped inside a beaker. So we can consider there is a big beaker where there is some water in it, and then if you drop of ink, and then as time goes on, this ink is dispersed around the beaker, and this color is uniformly distributed throughout the water, and then basically entropy here is close to zero, and then entropy here is maximized, uniform distribution, basically entropy of a uniform distribution. So in this case, entropy is non-decreasing or increasing. So that's the thermodynamic way of, that's the second law of thermodynamics. But in our case, in information theory case, as we have seen in previous case, you can design a system whose entropy increases or decreases. It all depends on your initial distribution and the stationary distribution. Stationary distribution depends only on the transition matrix, not on the initial distribution. Because this is a Markov chain, it forgets the initial distributions. Okay, so that's what I mean. What I mean by the entropy of a Markov chain. Okay.